All right, ladies and gentlemen, we are looking at section 11.3 today on geometric sequences. So this is the second of the two very common sequences that we deal with in mathematics. The first being the arithmetic sequence that we talked about last time. Now it's the geometric sequence. Now the arithmetic sequence, as you saw last time, was the discrete version of the linear relationship. It's just, if you plot the points, they fall in a line. The geometric sequence is the discrete version of an exponential function. So let's give the definition. A geometric sequence is one in which any term divided by its previous term is a constant, and that constant is called the common ratio. And since we use the word ratio to represent this constant, we typically denote it with the letter R as we're writing our formulas. Okay? So the difference between the arithmetic and the geometric sequence is the arithmetic sequence is one in which any term is the previous term added with a constant. The geometric sequence is the previous term is multiplied by a constant to get the next term of the sequence. So as opposed to in the arithmetic sequence, where when you would write the sequence, you would have a1 plus, or a1, then a1 plus d, then a1 plus d twice, then a1 plus 3d's, and so on. Now you're going to be multiplying by a common constant, and so this will look like first term, then the second term is the first term multiplied by that common ratio. The next term is the previous term multiplied by r, which means another r, multiplied by another r, and you go on and on like this. Okay? You could understand this as a recursively defined function as well this way, written recursively. A1 is the first term, and then a sub n is simply the previous term multiplied by r, and that works, of course, for n bigger than or equal to 2, meaning not for the first term. And there's your recursive definition of a geometric sequence. Okay? Now, written explicitly, which is our author's way of saying written as a formula, the way you would write this is an is the first term times r n minus 1 times. So when n is 1, you don't multiply by an r. When n is 2, you multiply by an r once, and so on. And so these are the formulas for this section. And that's basically it that we need to talk about before we start actually working some problems. So let's try problem number 6. In the exercises, the author gives you this sequence 1, 3, 9, 27, 81, and says find the common ratio. Now, the way you find a common ratio is assuming there is a common ratio. All you have to do is take any two adjacent terms, 81 and 27, or 27 and 9, or 9 and 3, or 3 and 1, it does not matter, any two pairs, and divide the next by the previous. So for example, 3 divided by 1, there's your common ratio. Now that would have worked for 9 divided by 3, 27 divided by 9, 81 divided by 27. It doesn't matter which pair you take, you're going to get the common ratio, assuming this is a geometric sequence. In problem number 8, let's do that one over here. The sequence we're given is -2, -1/2, negative 1/8, negative 1/32, negative 128th, dot, dot, dot. Again, just take any two. The next divided by the previous, so negative 1/2 divided by negative 2, and that's going to give you the common ratio. So of course the negatives cancel. 1/2 divided by 2 is 1/4. There's your common ratio. Negative 1/32 divided by negative 1/8 would have given you the same thing. Negative 1/8 divided by negative 1/2 would have given you the same 1/4. Negative 128th divided by negative 1/32 would have given you 1/4. It doesn't matter which pair you use. Okay. All right. Now, in problem number 10, you're asked to determine whether the sequence is geometric. If it is geometric, find the common ratio. So in number 10, you're given the sequence 5, 5.2, 5.4, 5.6, 5.8, dot, dot, dot. And you're asked, is this a geometric sequence? Well, it's certainly not, because all we're doing is adding 0.2 every time. This is an arithmetic sequence, in fact. And so the way to show this is not a geometric sequence is to try to find a common ratio. 5.2 divided by 5, and you can certainly use your calculator for something like this. It's not a problem. So we type in 5.2 divided by 5, and we get 1.04, and then take 5.4 divided by 5.2. 5.4 divided by 5.2, and we get 1.03846, 1.038, dot, dot, dot. These are not the same. So, not geometric. Can't be a geometric sequence if you don't have a common ratio. Okay? All right, let's take a look at problem number 14. In this exercise, write the first 5 terms of the geometric sequence, given the first term and also given the common ratio. So in 14, we're given the first term is a1 equals 8, and we're given the common ratio is 0.3. So writing the first 5 terms, well, we already got the first. The second is 8 times the common ratio. 8 times 0.3 is 2.4. The third is the previous, 2.4 times 0.3. So take our calculator if we want to make this easier on ourselves. 2.4 times 0.3, and we get 0.72. The fourth term is the previous term, 0.72 times 0.3. So multiply that previous term times 0.3, 0.216. And the fifth term, 0.216 times 0.3. Multiply the previous term times 0.3, you get 0.0648. There are the first 5 terms of the geometric sequence. Okay. Now let's try number 16, where we're asked again to give the first 5 terms of the geometric sequence, but this time they give us instead that a sub 7 is 64 and a sub 10 is 512. So they don't tell you the first term and they don't tell you the common ratio, but they want the first 5 terms written. So how would we do such a thing? Well, an easy reasoning that we could use is to get from a sub 7 to a sub 10, we had to multiply by the common ratio 3 times. So 64 times the common ratio 3 times is what gets us to 512. That means the common ratio is 512 divided by, or cubed is 512 divided by 64. So you take 512 divided by 64 and you get 8. The common ratio cubed is 8, means the common ratio is 2. So we found the common ratio. Okay? Now, one way to reason through this would be to say, okay, if I know a sub 7 is 64 and I know the common ratio is 2, then a sub 6 would have had to have been 64 divided by 2, right? A sub 6 would have been 32. That means a sub 5 was 32 divided by 2 is 16. A sub 4 is 16 divided by 2 is 8. A sub 3, 8 divided by 2 is 4. a sub 2, 4 divided by 2 is 2, and a sub 1, 2 divided by 2 is 1. There's the first 5 terms. Okay? So that's kind of a brute force way to do it, a little inelegant, but it certainly worked easily for this problem because we were so close to being at A5. We were only at A sub 7. Another way we could have approached this is once we knew the common ratio, we could have said, okay, now let's use my formula. A sub n is going to be the first term times r to the n minus 1. And I know the common ratio r is 2. Okay, so I know my formula looks like that, right? And I know a sub 7 is 64. So 64 divided by 2 to the 6 is a sub 1, and of course that works out to be 1. And so we found the a sub 1 term. Now once you know the a sub 1 term, you just keep multiplying by 2 to get the rest of them. Okay? So there's another approach to solving that problem. I think I like the brute force way for this one, just because a sub 7 again was so close to the sequence a sub 1 through a sub 5 that we needed to figure out. It was quite easy to do it that way. All right, let's try problem number 20. And 20, they give us a sequence. A sub n equals -1, 2, -4, 8, and they assure us this is a geometric sequence. So that means, of course, I can just go ahead and find the common ratio, 2 divided by -1. There's my common ratio. I know a sub 1. And so I know the general form of this a sub n is a sub 1 times r to the n minus 1 is going to be -1 times -2 to the n minus 1. And now they say write down the 12th term is what they want. A sub 12. Well, that's -1 times -2 to the 12 minus 1. That's -1 times -2 to the 11th power. A -1 and a -2 to the 11th multiplied together will be positive because you'll have 12 of them, negative signs in total. So raising 2 to the 11th is 2048. There's the 12th term. All right, let's take a look at number 24. Write a recursive formula. For the geometric sequence in 24. A sub n is the sequence -1, 5, -25, 125, ... And so it's very easy to see that the common ratio, 5 divided by -1, is -5. And of course, a sub 1 is -1. And so we know how to do this as a recursive. We write a sub 1, and then we write a sub n is the previous term times the common ratio. And there is the recursive formula for this. Very straightforward to write those recursive formulas. Let's try number 26. Similar question. The sequence we're given, 14, 56, 224, 896, ... In effect, as long as they tell you it's a geometric sequence, you only need the first two terms. You don't need these, right? Because all you have to do is, once you know it's geometric, to find that common ratio is divide. And you know the first term. So a sub n is the a sub n minus 1 times 4. And there is your recursively defined sequence. Try 28, so we get to practice with some decimals. 0.61, 1.83, and again, all the rest of these I don't really need, but 5.49, they tell us, 16.47, ... You're just going to take 1.83 divided by 0.61 to get the common ratio. That's 3. And then you say a1 is 0.61, a sub n is the previous term times 3. And here is your sequence written as a recursively defined function. Okay, let's try number 34. Write an explicit formula this time. Explicit formulas are in general more useful to us in mathematics than recursive ones. So they give us a geometric sequence, so of course you know to divide, you get the common ratio. You know a sub 1 is negative 2, and so the explicit formula here is a sub n is the first term times r to the n minus 1. That means a sub n is negative 2 times your r 2 to the n minus 1. There's your formula. All right, let's take a look at problem number 40. Write an explicit formula in number 40 for the sequence a sub n is 2, 1/3, 1/18th, 1/108th, and so on. And again, as long as they tell you it's geometric, you just need the first two terms. R is 1/3 divided by 2 is 1/6. So the explicit formula, you know a1 is 2. You know the form is a sub n is a1 times r to the n minus 1. So you know that a sub n is the first term, 2 times the common ratio, 1/6 to the n minus 1. And there's your formula. Okay. Let's find in number 44, given this geometric sequence, a sub n equals -1, 3, -9, ... up to 2,187. The question is, how many terms are there? In other words, how far does n go? This is n is 1, n is 2, n is 3. Where does it stop here? Okay. All right, so the way to do this is to come up with the formula, and that means find the common ratio, find the first term, write the general form. So that's -1 times -3 to the n minus 1, okay? And then say, okay, what is the value of n that makes this equal 2,187? Solve for n. So of course, if you divide both sides by -1, you get that. And so the question is, to what power would you have to raise -3 to get 2,187? -2,187, okay? So basically, 3 raised to the 7th power gives you 2,187, so that means that here, n minus 1 is 7, so n is going to be 8. This is the 8th term in the sequence. Okay. All right, the final question I'm going to look at in this section is number 52. Okay, and in 52, you're asked to do this kind of interesting thing. Use explicit formulas to give two examples of geometric sequences whose 7th term is 1,024. In other words, we want to find two different geometric sequences who have the same 7th term. Okay? And so when I look at 1,024, I'm thinking powers of 2, naturally, right? So I want to start my first example. I want to use the common ratio of 2. Okay? And so a sub n is going to be the first term times r to the n minus 1 is going to be the first term times 2 to the n minus 1. So a sub 7 is going to be the first term times 2 to the 7 minus 1 is 6. And 1,024 is a sub 1 times 2 to the 6. Then a sub 1 is 1,024 divided by 2 to the 6. 1,024 divided by 2 raised to the 6th power is 16. Okay, so this would be the sequence. This example would be the sequence where the first term is 16 and the common ratio is 2. Okay, my second example, I think about a different common ratio. Instead of using a 2, what could I use that's also easy? Well, 4 would work nicely as well. So a sub n, again, is a sub 1 times r to the n minus 1. So now that's a sub 1 times 4 to the n minus 1. A sub 7 is a sub 1, therefore, times 4 to the 6, where a sub 7, again, has to be 1024. So that means that a sub 1, this time, instead of dividing by 2 to the 6, you divide by 4 to the 6. 1024 divided by 4 raised to the 6, and I get 0.25, or 1/4. So a sub 1 is 1/4, and r equals 4 would be a second geometric sequence that has the same seventh term of 1024. Okay? All right, that's it for geometric sequences. Please work hard on those homework problems. Get to understanding of this very, very commonly used sequence in mathematics. We use this extensively in math. In fact, in Calculus 2, I've just spent the last several weeks working with this sequence with those students as well. So you definitely will see this again if you go into Calculus.